Hello. Today we will be solving inequalities by adding or subtracting. This is our second lesson in Chapter 2 Algebra. Let's think about what we learned in Chapter 1. In Chapter 1, we learned that we can graph an inequality by using the disk method. This is just a way to help us the steps to follow when graphing. For instance, let's say we have the inequality x is greater than 2. So to graph x is greater than 2, we start with a number line. D stands for draw. Draw a number line and a circle at the end point. The end point is 2, the number we're comparing x to. Remember, x stands for all real numbers. So we're going to draw a circle at the number 2 on the number line. Notice I'm drawing the circle on the line, not above the line. The I stands for include. Look at the inequality sign. The inequality sign is greater than. So the question to ask yourself is 2 greater than 2? No, it's not. But anything above 2 is. So the number 2 itself is not included, therefore we will leave an open circle. The S stands for shade. This means shade in the correct direction. So we want to find on the number line all numbers greater than 2. That would be to the right. We're going to shade to the right. That's where we find numbers that are greater than 2. Here's a little hint for you. If you put the variable on the left in your inequality, then you can shade in the direction of the arrow. The arrow is the greater than sign. It's pointing to the right, so we shade to the right. Remember, this only works if your inequality symbol, if your variable is on the left. The C stands for check. Substitute a value on the solution side to check that the inequality sign is true. So this means think of a number that's in the shaded region. So to the right of 2. For example, the number 3 would be in the shaded region. So to see if 3 is a solution, put it in for your variable. Yes, 3 is greater than 2. So we have shaded in the correct direction. These same principles apply when we're solving inequalities that have addition or subtraction involved. Here we go with our properties of inequality. The first one is the addition property of inequality, which states that you can add the same number to both sides of an inequality and the statement will still be true. So let's use our example x greater than 2 again. If x is greater than 2, I can add the same number to both sides. For example, the number 3. 3 plus x is greater than 2 plus 3. I've added 3 to both sides. It's still true. To show you this works without variables, let's just create a statement such as 5 is greater than 2. Yes, we know 5 is greater than 2. If I add 3 to the left and 3 to the right, I get 8 is greater than 5, and that is still a true statement. The same works for subtraction. You can subtract the same number to both sides of an inequality. The statement will still be true. So for example, if I have x greater than 2, and I subtract 3 from each side, then the resulting statement is still true. So x minus 3 would be greater than negative 1. Again, let's do the same thing with real numbers. So let's start with, let's do 5 again. 5 is greater than 2. Let's subtract 3 from each side. 5 minus 3 is 2. 2 minus 3 is negative 1, and positive 2 is still greater than negative 1. I've subtracted the same number from both sides. My inequality is still true. Let's work some examples. So today we're going to be solving inequalities that involve addition or subtraction. Let's look at this example right here. X plus 12 is less than 20. You solve these in the same way you solve equations. If this were an equation with an equal sign, to get x by itself, you would subtract 12 from each side, which we just learned we can do. That isolates my variable, giving me x is less than 8. And that is my solution. So on my number line, I want to shade all real numbers less than 8. I'm going to put a circle at 8. This is called my boundary point. It will be an open circle because 8 is not less than 8. That's my boundary point, but it is not part of the solution. I have my variable on the left, so my arrow points to the left. And on the number line, I'm going to shade all numbers less than 8, and I shade it in the direction of the arrow. To check this inequality, there's two things you have to do. First, check the endpoint. To check the endpoint, think of this as x plus 12 equals 20. Put your boundary point in. My boundary point is 8. 8 plus 12 does equal 20. So my boundary point is correct. My endpoint is correct. And then I have to check the inequality symbol. To check the inequality symbol, pick a number on the number line that's less than 8. For example, 0 is less than 8. Put that in your original equation, x plus 12 less than 20. So if you put 0 in, you get the resulting inequality. 12 is less than 20, which is still true. So my inequality symbol is correct and it's shaded in the correct direction. Here's another example involving subtraction. How do you undo subtraction? By addition. What do you add? You add the number that was subtracted. So here I have d minus 5. To undo the minus 5, I add 5 to each side, just as I would with an equation. But instead of equal to negative 7, I have d is greater than negative 2. Now I'm going to use the disk method. I drew the number line already. I'm going to put a circle at negative 2. Okay, negative 2 is not part of the solution set because it's greater than. So I'm going to shade all the numbers greater than negative 2, and I find those to the right on the number line. Notice I have my variable on the left, my arrow points to the right, I shade to the right. So here's my final solution. It's all real numbers greater than negative 2. To check the endpoint, I put a negative 2 in for D. Negative 2 minus 7 is negative 7, so the endpoint is correct. And then I'm going to pick a number in the shaded region. I'm going to pick the number 4, put it in for the variable. 4 minus 5 is greater than negative 7 because negative 1 is greater than negative 7. And I have the correct inequality symbol. I shaded in the correct direction. Another example, I left my variable out of this one. Well, let's just make it up then. Let's do 0.9 plus x is greater than or equal to 3/10. I want to get rid of the 9/10, so I'm going to subtract 9/10 from both sides. Remember, I'm adding its inverse. These are decimals, but that's okay. Decimals are numbers too. That leaves me with x, gotten rid of the 9/10, greater than or equal to, whoops, I have a positive and a negative, so remember, you're going to subtract the 2, but your answer is going to be negative because you are taking away the absolute value of the bigger number. So that's x is greater than or equal to 6/10. To graph that on the number line, I'm going to estimate the location of 6/10. I'm going to estimate it right here. This time we put a closed circle because 6/10 is equal to 6/10. This bar underneath represents greater than or equal to. So if it's possibly equal to, we put a closed circle. A bar underneath means a closed circle. Our arrow points to the right. We're looking for numbers greater than 6/10, so we shade in the positive direction. There's our answer. To check this, we check the endpoint by putting the number 6/10 in. Oh, and I forgot to put my negative sign. See, if I had not checked, I would not have caught this. So let's back up. See, 6/10 plus 9/10 is not 3/10. My endpoint doesn't check. Here I forgot my negative sign, so that means instead of starting on this side of 0, I'm starting on this side of 0. I'll move that over a little bit. That's why we check our answers. So it starts on the left of 0 and shades to the right. It's still a closed circle. Now I'm going to put in a negative 6/10. That's much better. Now I get the right answer. 9/10 minus 6/10 does equal 3/10. My endpoint checks. I'm also going to check to see that I shaded in the right direction. I'm going to choose the number 0 because 0 is part of my solution, and 0 is just a very nice number to work with. 9/10 plus 0 equals 9/10, and 9/10 is greater than 3/10. I have shaded in the correct direction. Again, it's very important to check your answers. Here's an example that's a word problem. I think this is our last example. Sandy has a gift card. She's already used $14 of the total value, which was $30. Write, solve, and graph an inequality to show how much more she can spend. So we're going to, what are we looking for? We're looking for amount left to spend. Okay. So she spent $14. How much more can she spend? Well, $14 plus the additional that she can spend. How does that relate to 30? Can she spend more than 30? No, she only has 30 to spend. Can she spend less than 30? Yes, she can spend $30 or less. Can she spend equal to $30? Yes, she can spend the whole amount. So I'm going to put an equal sign underneath it to show she can spend less than 30 or she can spend equal to 30. Now, before I draw my number line, I'm going to solve for x by, yes, subtracting 14 from each side. It gives me x is less than or equal to 16. So my boundary point is 16. I think that I will count by 2s. I'm going to put 0 here. 2, 4, 6, 8, 10. You don't have to have this many numbers on your number line. It's just that it was already drawn for me. So now I'm going to put a circle at my boundary point, which is 16. Will it be open or closed? Well, it could be less than 16 or equal to 16. It will be a closed circle. I have my variable on the left, so I'm going to look at the arrow. It points to the left. I'm going to shade in the negative direction. So I'm looking for amounts less than $16. But wait, does it make sense to have a negative amount? Can she spend a negative amount of money? No. So actually, what numbers make sense in this problem? The numbers that make sense in this problem, sorry about my eraser, there we go. The numbers that make sense in this problem start at 0. She's not going to spend less than $0 on her card. So we're actually going to end this particular problem at 0. This is a real life application. She can spend anywhere between $0 and $16 and therefore use her gift card. And that's all for today. When you come in tomorrow, you'll be ready to practice these problems. Thank you.